instead, I want to dig a little bit more into something that Neil touched on, which specifically is deep learning. But before I do, I want to tell you my story of how I came to deep learning and originally through machine learning. So for those of you that don't know, machine learning goes back a long way. It goes back to 1956 when this guy, Arthur Samuel, managed to get this IBM mainframe to play checkers at a level better than he could. Rather than programming it in a traditional way by telling it step by step how to play checkers, he said, play against yourself and figure out what works. And that was very successful. When IBM, Thomas J. Watson, announced the success of this program, IBM's share price went up by 15%. So machine learning has a long history of commercial success as well as academic success. My personal background actually was starting off in the world of philosophy and then in business strategy consulting. I then ran a couple of companies, an email company, an insurance pricing company. So quite a different kind of background to perhaps a lot of people in this field. But then, as Salim said, surprisingly enough, when I, after selling my second company, decided to try competing in data science competitions professionally, I was surprised to discover I got to the #1 ranking in the world, which is very surprising to me as somebody that didn't have a technical background. And it really coloured a lot of my feelings today about what it takes to be effective in using machine learning to solve your real-world problems. And that's really what I want to talk to you today about. Based on that experience with Kaggle, I became their first investor and eventually became their president. I then met Peter Diamandis and joined the faculty here of Singularity University, where I've been teaching for a few years. I then, a few years ago, took a year off. And when I say I took a year off, what I actually did was I spent a year doing research. And the research was into what are the biggest opportunities in the world right now for these technologies that I've been learning about. To give you a sense of where I was coming from here, based on my time at Kaggle, an article based on an interview with me came out saying specialist knowledge is useless and unhelpful. This was perhaps a bit of overkill, but it certainly touched on how I was feeling that all the people winning the top machine learning competitions, solving previously unsolved problems, were always people with no domain expertise in the area that they were solving these previously unsolved problems. There was, however, something interesting, which was that they pointed out that or I pointed out at the time, this was 2012, that the difference between the good competition participants and the less good was the information that they feed the algorithms. And that still required a lot of creativity and insight, and that was really the basis of the work that I was doing at that time. This is a great example of what I mean. So this is a 2012 algorithm that was developed to predict the survival time of people with breast cancer. These pictures, some of you might recognize, these are pictures of breast cancer slides under a microscope. And what happened was a team of data scientists at Stanford and a team of pathologists at Stanford got together and came up with hundreds and hundreds of ideas about what kinds of things could an algorithm look for that might indicate higher or lower survival of cancer. And then the programmers programmed all of these hundreds of, they're called features. They took then these hundreds of features and looked at the difference between patients who are alive after 5 years, patients who are dead after 5 years, put it through a machine learning model, and that then predicted the survival rate of the different groups. The result of this was an algorithm that was more predictive than pathologists at guessing the survival rate of these patients with breast cancer. So this was a big deal back in 2012, but it was a lot of work. And that was certainly my experience of competing in Kaggle competitions, was it was a lot of work to kind of come up with and program the kinds of features, even when machine learning could then go and figure out how to combine them together. So that's machine learning from 1956 until kind of 2012 on the whole. Then in 2012, something really interesting happened, which was one of the competitions that I was running at Kaggle was for Merck, the big pharma company, and it was trying to do automatic drug discovery. And this guy, Geoffrey Hinton, who is the father of deep learning, his team won the competition. They joined with only 2 weeks to spare, Nobody on their team had any background really in biology or life sciences. And they came up with an algorithm that was better than any previous automatic drug discovery algorithm in the world. Much better. And the trick was that they used this technology called deep learning. This was such a big deal that the New York Times actually featured him on their front page article a few weeks later. I'd been very much aware of deep learning for at least 20 years, but I was not aware that it could be used for something this commercially vital or this kind of this mainstream as drug discovery. So to give you a quick sense of why this is so exciting, what is deep learning? Deep learning is an algorithm for machine learning, so an algorithm that can let a computer learn how to solve your problem, which has three critical features. The first is that it has an infinitely flexible function. What that means is we have mathematically proven that a deep learning algorithm can solve any given problem, whether that problem be automatic drug discovery or playing Go or whatever. These, as far as a computer is concerned, these are all mathematical functions to be solved. Deep learning then has an all-purpose parameter fitting algorithm, which means that if you give data to the infinitely flexible function, it will modify itself to solve the specific problem that you've asked it to solve. That had actually been around for quite a few decades. The thing that has happened recently is the addition of fast and scalable. As Neil mentioned, there is now hardware such as the tensor processing unit from Google. With this kind of hardware, compared to a few years ago, we can now build these deep learning models which are thousands of times bigger or even millions of times bigger than they used to be. And critically, when you make these models bigger, they suddenly hit the point where they outperform all previous state-of-the-art results. So the particular type of function that we use is something called a neural network. The particular kind of way of fitting the parameters is something called gradient descent. And then the particular way of making it fast and scalable is by using these kind of special hardware such as tensor processing units or more broadly GPUs, which are used for playing computer games. It turns out that the thing necessary to play a computer game is very, very, very similar to the thing necessary to train a deep learning model. So most of the world actually is using GPUs. Things are moving quickly in the hardware side. In fact, people are starting even to look at quantum neural networks. So on that fast and scalable side, things are getting better and better and better. So a few years ago, during this year I spent off, I was really looking at like, wow, okay, what was going on then? This is 2012 / 2013. And what does it mean? And I thought, well, if it's really true that this era of machine learning, and particularly deep learning, means anybody can do anything, then my goal should be to find the most important problem in the world to solve. And at a World Economic Forum event, I saw this chart, which kind of changed my life, which said that based on current infrastructure, it would take 300 years to train enough medical experts to meet the world's needs. And I thought, that's not okay. And I started looking into medicine during the year of research I did, and I discovered it turns out that diagnostic medicine is basically a data science problem. Once you've collected the information about a patient, you're basically analysing their data compared to previous patients to try and identify patterns. And I knew that this was exactly what deep learning had recently become better than any other system at. So what I did was I started a medical company. To say that people were skeptical about this would be an understatement. I guess this was August 2013, I launched Analytic I was the sole founder, and I said, this company, this was the website that I launched with, this company is going to bring deep learning to medicine. It was the world's first deep learning for medicine company, and the idea was, hey, you know, what would happen if we treated medicine as a data science problem and applied deep learning to it? Some people felt that my medical experience was a little short. And I've got to admit, I was kind of terrified as well. It's unusual to go into a field you know literally nothing about. But I think when you claim something, you have to be prepared to back it up and give it a go. So I did. And much to my surprise, within 2 months, I had hired 5 other data scientists, and we had built an algorithm which smashed the state of the art in lung cancer diagnosis, and in fact beat 4 of the world's best human radiologists working as a panel at predicting the malignancy of cancer. And so this ended up getting covered by CNN. It turned into a very successful company, which is still going today. So suffice to say, I got even more excited about deep learning. At the end of that year, I actually gave a talk, which has now ended up on TED.com. And if you want to learn a bit more about this history of deep learning, you can go and check it out. So, you know, that's my story, is kind of going from theory of saying, okay, I know quite a bit about machine learning, and I can kind of see what deep learning ought to be able to do in theory, and let's give that theory a try on the problem that seemed like the most important problem to solve in the world that I could find. Since that time, deep learning has gone on to transform everything that it touches. And so I'm going to give you a whirlwind tour. For example, Inbox by Google will take any email that's sent to you and automatically suggest replies for it. These are not pre-canned replies. These are written from scratch by Google Inbox's deep learning algorithm. Today, 15% of replies from Google Inbox are automatically generated by the system. In terms of most, 15% of these people using the system just take the pre-canned reply and send it off. Skype Translator is now live. This is a deep learning system that translates your voice to one of 7 other languages in that voice. Increasingly, they're even adding the modulation of the original speaker. They're adding more voices. Again, this is a deep learning-based system. You may have seen these artistic style applications. They're quite incredible. You can take any photo and any piece of artwork, and this deep learning algorithm will understand the essence of each and combine them. So you can see, for example, in this case, how it's kind of figured out the geometry here and said, oh, I could connect up her eyebrow and her shoulder, and I could kind of create a little glow out of her bun and so forth. It's important to realize all of these applications I'm showing you are not hand-programmed in some way. These are all just learnt by computers automatically using deep learning by giving data. There's me. This is actually not a genuine Van Gogh, so I'm not going to try and sell it to anybody. This is actually one of my favorite artistic ones. This is called Neural Doodle. You can get this online. Over here, you can see somebody drawing a little sketch of something. And over here, you can see that when they then said, please produce this as an impressionist painting, that was the result. Again, this is not programmed. This was learnt from data. You could also download Microsoft's image composite editor, and if you have a rather crappy attempt at a panorama like this one, you can feed it to the system and it will automatically hallucinate a piece of image that might work for you. So actually I was chatting to Steve Jurvetson, who is currently competing with me in the other room at the moment, talking in the other room, and we were trying to look through here to kind of say, okay, if you didn't know this, could you figure out that this was, none of this area was real? We kind of saw a few examples, but it's not at all easy. You can see over here, for example, it's even hallucinated a car. So this is what happens when deep learning can look at millions of images and learn what the world looks like. So this is one of my favorite pictures. A couple of weeks ago, Jeff Dean from Google produced this graph showing the use of deep learning at Google. Now, Google were probably the first to really invest in deep learning. And if you think about it, they do a lot of different things. They throw balloons up in the air to try and provide internet. They lay fiber optic cables. They do search. They do all kinds of things. They provide phone operating systems. So this chart shows from 2012, which is really when things kicked off, till now, what has been the use of deep learning in terms of how many software programming directories does it appear in. This is just a purely statistical test. And you can see this classic hockey stick shape. Now, the reason I think this is critical is because this is a microcosm of the world, right? This is what every company is going to look like over time, or at least the ones that are going to succeed. And the reason that this hockey stick has happened is I know from my friends at Google is every time their kind of their internal deep learning consulting unit goes to a different group at Google and says, let's try using deep learning, they get massively successful results and they start using it and then they become evangelists, and that's why you kind of get this shape. So, in terms of the overall world level of deep learning, we're still down here. but the most earliest adopter is certainly well down the track. Deep learning is now more effective at identifying the contents of photos than humans are. This was actually nearly a year ago now. Humans are on this data set of 1.5 million photos. If you randomly grab a few and ask a human, what's this a picture of, they make about a 5.3% error. As of about a year ago, deep learning was down underneath 5%. And in fact, in the last few weeks, this is now down to 3%. So computers are nearly twice as good at recognizing the content of photos based on deep learning. As Neil said, Baidu has a system that is better than at understanding speech. Again, that's a deep learning system. It's trained end-to-end with deep learning. So it's important to recognize that Baidu's system does not have a whole lot of hand-coded features or hand-coded pre-processing. It's a deep learning system that takes the input waveform and it learns it directly. This has resulted in some pretty interesting applications. In Russia, there's a system called FindFace, which is a deep learning algorithm that anybody can use on their largest social network. One guy took it out on the Russian subway, took photos of people, and found that with 70% reliability, he could find who that was a photo of, which is kind of creepy, particularly when you consider if you go to this website, they call this a dating app, which is kind of terrifying. So for those of you that watch Silicon Valley, the Wiseman score has now been beaten. Last week, Google announced that they have a system that, compared to the prevailing standard for image compression, has massively beaten it. And again, it's a deep learning algorithm. This is kind of really showing this idea that any function you can come up with, which in this case is take a picture, create something that's a smaller version of the same picture, that's just another function. You can throw it at a deep learning algorithm. And every time I know of people throwing something at a deep learning algorithm, they smash the state-of-the-art results. So in this case, as of a couple of weeks ago, the leading approach to compression has now been handily beaten. One of the things that I love is that we're just starting to see people outside of the Googles of the world really successfully use deep learning. This is a system which massively improved the state-of-the-art at classifying skin lesions. And the nice thing is that the people who did it are not deep learning people. They're people from a classic medical image analysis lab. For harder to recognize types of lesion, the previous state-of-the-art was only 15.6% accuracy. They have quadrupled it in a single step. So it's really nice to see that we're starting to see deep learning become a little bit more accessible, and people kind of outside of the machine learning world are starting to use it, and every time they do, again, they get massively improved results. Another great example with this was a group of people at Virginia Tech who have a system that can double the effective coverage area of a radio signal. And so you can imagine this is worth billions and billions of dollars. And again, they did it by applying deep learning to the question of improving radio modulation. It's also being used for fashion. It's actually being used very widely. In fact, Stitch Fix, which is a successful local company, has one of the top machine learning groups in the country now, probably in the world. And this approach of using deep learning for helping people suggest what they might want to try wearing or combining outfits or so forth is a rapidly growing area. We're seeing it widely used in medicine, not only my company, previous company, Analytic, but 50% improvement in predicting whether an infection will result came from applying deep learning to looking at a heart rate time series. The question of automatic drug discovery has gone a long way since that early Merck competition I mentioned. Now a group of people at Google and Stanford a few months ago got together and again smashed the state of the art in this in an academic setting. Finding the Higgs boson is something that deep learning has made huge inroads into. We've already heard from Neil about the AlphaGo success. That was another deep learning algorithm. It's interesting the way this worked actually was they basically treated it as an image analysis algorithm. So they took the picture of the Go board, which has lots of checks on it and a bunch of different circles where the stones are, and they basically trained the deep learning algorithm to be able to look at the board and recognize whether it was a good board or a bad board by feeding it hundreds of thousands of examples of previous boards from previously played games that were in a database. So again, it's quite a nicely kind of simple approach to solving a very, very challenging problem. This is not just being used for playing games, mind you. DeepMind immediately has given back their $500 million purchase price by reducing cooling bill by 40% at Google. And this was done by taking a deep learning algorithm to the sensor data from their data centers and making recommendations about different ways that they could handle the cooling. So, here's suddenly billions of dollars in a single go. So even within a company, there's lots and lots of ways to improve simple logistics using deep learning. So in some ways, that might kind of sound scary. It's like, oh my goodness, deep learning is everywhere. But what I actually want to do today is convince you to give it a go, because I still think 99% of the world is untouched. I think we're at the same spot with deep learning as we were with the internet in about 1991. Which is lots and lots of examples showing that the internet's going to be successful in 1991, but most people not using it for anything much at all. To show you an example of this, I'm going to show you 4 examples of deep learning. Here is one which was done by MIT and Shell for feature detection for geophysical features to help with oil finds. Actually, this might be shale gas finds, actually. Here's one from Amazon, which was a winning entry in quickly unstacking shelves. Here is one from Harvard Sustainability and Artificial Intelligence Lab for automatically mapping the poverty of the world. And here is one from something called the Zebra Rally for automatically identifying which zebra is which in order to create a Uganda-wide population count of zebras. Why are these 4 interesting? Because these are 4 that hit my inbox in the last 1 week. So you can see the speed at which these things happening is great. It's kind of like, these are not 4 I particularly curated. I just wanted to say, like, it's still in the case where somebody in the world of zebra tracking said, well, I wonder what would happen if we tried deep learning. Ditto in poverty analysis, or ditto in Amazon stacking, or ditto in looking at seismic analysis. Every time somebody applies it, it seems to work. So there's still a huge number of opportunities, which is why I say the time is now to give this a go. And so when I say this to people, I always like to say, so why not you? And I get all kinds of answers to why not you. One funny one is, it's too trendy. It's just a fad. Actually, there's a very sound mathematical foundation. There's something called the universal approximation theorem, which actually proves that this mathematical architecture can solve any given problem. Perhaps more importantly, empirically, we see state-of-the-art results in peer-reviewed journals every time deep learning is applied to something. So it's trendy for a reason, and it's not going away. Some people think that you need to be Google or Baidu scale to be successful at this. Actually, a very fast GPU costs $700. Furthermore, you'll generally get 2 or 3 free computer games when you buy one, so it's extra good. And in my experience, a single computer is still best for most deep learning tests that I've been doing on state-of-the-art results. So it's really not expensive at all. And then people say, well, I don't have Google or Baidu level data. Actually, as I'll show you in a moment, you can use existing models that people like Google have trained to help you use your data, and you actually don't need much data at all. Something which maybe people don't say, but they think is, oh, we're a big company, this is too early for us, we can't be on the cutting edge. As I'll show you in a moment, early adopters win. You can't afford to sit back and wait for this. This is an exponential technology, so by the time you've waited, you'll be way too late. Deep learning has already proven itself. Finally, people complain that it's too hard. It seems that everybody doing deep learning are Stanford machine learning PhDs, and all the papers are full of mathematical jargon. I think that there's a group of people that loves the fact that deep learning is so exclusive. It's actually very simple, and in a moment I'll introduce you to some new learning opportunities. So if you think about some of the early companies, do you know where IBM came from? IBM was actually originally the Hollerith tabulating machine. It was the very first punch card system used for tracking the American census back in the 19th century. And the Hollerith punch card system eventually turned into IBM, which is what it is today. GE, of course, came from Thomas Edison, who invented the light bulb, amongst other things. Microsoft came from the first computer basic system that was widely available. And of course, I remember clearly Amazon being really the first at-scale internet commerce provider. Generally speaking, it seems to me that there is a huge benefit to being the first into a space. So there's one good reason not to sit around waiting. I mentioned about not needing too much data. There's actually a couple of weeks ago, actually sorry, back in June, there was a great blog post showing step-by-step instructions on how to create a state-of-the-art image classifier using just a couple of thousand of images. And in fact, the state-of-the-art result in cancer diagnosis that I talked about, we only had 1,000 examples of people with cancer in our data set to get that state-of-the-art result. So we know that you don't need huge data sets. In fact, this is true of most machine learning systems. The Netflix algorithm that is used for recommendations, the group there, engineering group, tried adding more and more recommendations to the Netflix training set, and they found that the accuracy of the system flattened out and then stayed straight. So people use this term big data a lot. There are some things that need big data, but most things don't need big data. So the good news is, in terms of learning, I'm actually announcing this for the first time. We just launched this website, which is where you can actually go and learn deep learning. It doesn't require very much, but it does require some computer programming ability. It doesn't require any particular math ability. This will be at the Data Institute, which is sponsored by the University of San Francisco, that's just down the road. And this will be a 7-week course. The idea is I'm really trying to dedicate my life now to making deep learning accessible to everybody. So the idea of this course will be to make it so that everybody with an interest can learn deep learning. And one of the particular things that I want to do is increase the types of people that are learning deep learning away from just being white guys like me. Currently, it's not a very diverse field, and I'm hoping that we'll be getting in a lot of people that are from underrepresented groups as well. So that's my pitch to you. As Neil said, deep learning is a very exciting technology. I want to say it's not just exciting, but it's accessible. It's ready for you to use in your organization, and I hope that if you want to get started, you can send some people along here. Go to course.fast.ai, and you can sign up straight away.
All right. Jeremy Howard, thank you so much.